Our next talk is on the top 500, past, present, and future. The first three of the four authors, Eric Strohmeyer, Jack Dongarra, Horst Simon, are here with us today, but Martin Moyer was not able to travel out to join us. Eric Strohmeyer is a senior scientist and group lead of the Performance and Algorithms Research Group in the Computational Research Division at the Lawrence Berkeley National Laboratory. Eric Strohmeyer's main interests are in performance characterization, valuation, modeling, and prediction for HPC systems and large-scale scientific workflows. More recently, he has focused on the optimization of data-intensive workflows on large-scale systems and the application of machine learning for predicting performance. Strohmeyer was awarded the 2008 ACM Gordon Bell Prize for parallel processing research in algorithmic innovation. Together with Professor Dr. Hans Meyer, he devised and founded the Top 500 project in 1993, which started as a list of the most powerful supercomputers in the world and has evolved to a major source of information about trends in HPC. Eric has served as the main editor of the Top 500 since its beginnings, and the 50th list will be published at SC17 soon after this session. Jack Dongarra holds appointments at the University of Tennessee, Oak Ridge National Laboratory, and the University of Manchester. He specializes in numerical algorithms in linear algebra and parallel computing. He was awarded the IEEE Sidney Fernbach Award in 2004. In 2008, he was the recipient of the first IEEE Medal of Excellence in Scalable Computing. In 2010, he was the first recipient of the SIAM Special Interest Group on Supercomputing's Award for Career Achievement. In 2011, he was the recipient of the IEEE Charles Babbage Award. And in 2013, he received the ACM IEEE Ken Kennedy Award. He's a fellow of the AAS, ACM, IEEE, SIAM, and a foreign member of the Russian Academy of Science, and a member of the US National Academy of Engineering. Horst Simon is the Deputy Laboratory Director and Chief Research Officer of Berkeley Lab. The Deputy Director As the Deputy Director, he's been instrumental in the creation of new concepts such as the cyclotron road and CalCharge that support energy innovation and forge stronger connections of the national labs with industry. Horst Simon is internationally recognized for the development of sparse matrix algorithms, algorithms for large-scale eigenvalue problems, and domain decomposition algorithms. His recursive spectral bisection algorithm is a breakthrough in parallel algorithms. He has been honored twice with the Gordon Bell Prize, most recently in 2009 for the development of innovative techniques that produce new levels of performance on a real application, and in 1998 in recognition of superior effort in parallel processing research with others from Cray and Boeing. Martin Moyer is at Prometheus, the company behind the ISC Group and the conference co-chair of ISC High Performance that many of you know from its earlier name, International Supercomputing Conference. Martin Moyer has energetically expanded the ISC brand beyond Europe, and he has been influential in founding the spin-off events ISC Cloud and ISC Big Data. In 2014, Martin took over the Top 500 authorship from his father, Top 500 co-founder Hans Moyer. Thank you for being here.
Thank you, Padma. First, I'd like to, we would like to thank the organizers for giving us this opportunity to talk about the Top 500. In case you're not aware, this is the 25th year of the Top 500. In fact, it's the 50th edition of the Top 500, which we will talk about after this invited presentation in the Top 500 BOF. I'm going to talk about the beginnings of the Top 500 and the benchmark that led to it. When I'm having a casual conversation with somebody outside of our field, a question often comes up, what kind of hobbies do you have? And I often respond that my hobby is benchmarking supercomputers. And that's really the way I view the work that's gone into the Linpack benchmark and also the Top 500. So you're about to hear about the beginnings of my hobby. So in the beginning, as we heard from Gordon and from Wikipedia, the first modern supercomputer was a CDC 6600, and beyond that, modern supercomputing really started. In 1974, there was an effort underway to standardize how some of the mathematical kernels took place, and that was called the basic linear algebra subprograms. And those are vector operations, and today we reference them as the level 1 BLAs. In 1976, vector computers were emerging on the scene, with Cray being one of the dominant ones, but also Japanese vector computers were certainly very prevalent at that time. And vector operations coming through those kernels on vector machines were thought to be a good idea. As Gordon mentioned, we had him sitting here, the creator of the DEC-VAC system. That was a machine which was in common use in 1977. Linpack, in some sense, was created around June of 1974 when Jim Poole, the director of Argonne National Lab, of the Applied Math Division at Argonne National Laboratory, had the vision and insight to get together a group of people to construct a linear algebra library that would run on high-performance systems. And the idea was that package would be portable and efficient, use state-of-the-art algorithms, and deal with dense matrix computations. You have to realize at this time, we didn't have IEEE arithmetic. Computers had different numbers of bits that they were doing floating point arithmetic in, and coming up with a package that was portable across all of those machines was quite a challenge. In 1975, the participants in that project met at Argonne National Laboratory to lay the groundworks for the project. An NSF proposal was submitted, and we received funding to do that. Jim Bunch at the University of California, San Diego, Cleve Moeller, who's sitting in the audience, was at the University of New Mexico, Pete Stewart at Maryland, and I was at Argonne National Laboratory. Argonne was the center for the project, and we met during the summers to carry on most of the work of the project and coordinate things. In June of '76, we had the first draft of that software. We discussed the various conventions and style. In June of '77, the test software was developed, and we also constructed something called the Linpack User's Guide that would help users with that software. In November, that software was released. As a result of that package, I became an accidental benchmarker. In the appendix to that user's guide was a small table, about 20 machines, which I had collected the performance for solving a matrix of size 100. And that was through a Fortran implementation. I jotted down the time and then constructed the megaflop rate. And if you take a look at that slide there, or that table, you'll see pencil marks which have the megaflop rate next to the machine. And that was the first incarnation of the Linpack benchmark. I kept that table in my desk, and whenever a vendor would come to the lab, I would pull out that table and ask them, how well do you think you would do on this benchmark? And we sent the program to them, they ran it, and then the benchmark, or that table, expanded. So this is the group that did Linpack. So that's Jim Bunch on the right, Pete Stewart next to him, Cleve Moeller, who's sitting in the audience there, and that's a 1979 version of me with a little bit more hair. The car that you see there was my car with a Linpack license plate. That was when I was a graduate student in New Mexico with Cleve Moeller. A few years ago, we had an opportunity to get together again, and there are those four old guys with a little less hair and a little more white beards, I guess. Linpack sort of emerged over time. John Gustafson made this comment about matrix of size 100 was the initial matrix. Eventually, I had enough entries in that table to come out with a little report that had 70 machines reported for that matrix of size 100. And then the table was expanded to go beyond a matrix of size 100 to look at a matrix of size 1,000. And the basic algorithm that was required was Gauss elimination with partial pivoting. In 1989, the process changed because we were in a situation where we had much more powerful machines, and we needed to grow the size of the matrix. So the rule that was adopted in that case for the benchmark was to let the matrix grow to as large as you possibly can, solve that biggest problem you can on your machine, and look at the performance that you achieved for that large problem. And that became something that's called RMax for your architecture. In the year 2000, we put out an optimized version of the software, actually had a portable version of the software, which was a driver or a harness, which generated a matrix called your version of the Gauss elimination with partial pivoting and solve routine, and then the harness would look to see what kind of solution you achieved. And that really is the roots of it, of the top 500 list. Hans Moyer had a list of high-performance machines. That list basically was a table of machines. Vector machines were counted, and that worked well until the 1980s. But around the 1990s, the architectures became more diverse, as Gordon noticed. And having that list was a little bit awkward for just ranking the vector computers. So Hans approached me in 1992, along with Eric, to say we should merge the two lists into something called the Top 500. And that was the first Top 500 list was published in 1993. The #1 machine at that time was at Los Alamos National Laboratory. It was a thinking machine, CM5, and it had a performance that was listed around, I can't quite see it today, but it had performance was listed around 59 gigaflops, thank you. My laptop actually can perform the benchmark much faster than that thinking machine CM5 today. My laptop runs around 160 gigaflops, and that's a machine that I use primarily to read email. Now, I get a lot of email, but that performance is really going to waste in some sense. So the rules for the benchmark, we established some rules for the benchmark, and it's important to have rules. The algorithm has to be Gauss elimination. You're not allowed to change the basic kernel of the thing. You can't use Strasson's method to do that. It would disturb the operation count. The algorithm, you can't use a lower precision algorithm and try to refine the solutions. We reserve the rights to exclude matrices. You know, over time we have had situations where the vendors would try to bend the rules a little bit. I won't name names, but we had one vendor who had the -Linpack option in the compiler, where if you use that option, of course, it would do something really rather dramatic and special. So Linpack, or HPL, Linpack benchmark is widely recognized for high-performance computing today. It's gained a lot of prominence. In the 1990s, there was strong correlation with the applications that we had. Unfortunately, today, we don't see that same correlation. So there's a number of problems that we have with this benchmark. It no longer correlates with real applications. If you design a machine that does a good HPL number, that may not actually be a very good architecture for applications. So in the future, I think we need to be a bit careful about that. There's a number of good things I'll say about the benchmark. It's easy to run, it's easy to understand, to check the results. It stresses the floating point hardware. We have this historical database set up today that's very good. But you know, I like to say that if your computer doesn't do well on this benchmark, it's probably not going to be doing very well on your application program. So getting a high number is something that you would expect. The bad things about it, this benchmark is 40 years old now. The top 500 list is 25 years old. It's a computationally intensive problem, does very little data movement relative to the computations, and it no longer correlates with real applications. So it encourages perhaps poor choices in architectural features, and that's one of the unfortunate things about the benchmark. So there's a number of ugly things about HPL. It doesn't really probe the architectures. It only provides one data point. It constrains the technology, and if we're thinking about building an exascale machine and we use this to measure it by, that would certainly be an issue. And we're going to discuss that as we move on. Next, I'll turn it over to Eric.
Thank you, Jack. Good afternoon, everybody. So I'm going to talk for a couple of minutes now about two topics. The first one is really the roots of the top 500 as a market survey, which would have been the part Martin Moyer would have presented if he could have made the meeting. And then I'm going to present some special statistical methods, some special statistics, which we tried out to really aggregate the 25 years of history, all those 50 lists we have. So for the first part, we're going to go back again about 25 years, a few years more than 25 years. And things, of course, then late 80s, early 90s were different. An event like this, in this case the ISC, would actually take place in a very festive hall in the local castle. Despite the lack of any air conditioning, all the male participants would be expected to wear a suit and a tie. Even a freshly minted graduate like myself would not budge that trend. There was peer pressure. And there was the occasional oddball academic nonconformist which wouldn't do that. We all looked a little younger. The person on the right, that was Hans Moyer in those days. And Hans started the ISC, and in the first ISC in 1986, in the opening session, he presented the first statistics, the Mannheimer supercomputer statistics. And Jack already talked a little about them. So what in the middle of the 1980s, life was still very simple. If you were interested in compiling a statistics like that, there were only half a dozen of companies worldwide which produced vector mainframes, and all of their systems were by a factor of 10, give or take a little bit larger or faster than regular mainframes were. So there was a real gap in performance between those vector supercomputers and regular computers. So all you had to do for a supercomputer statistic is count those vector computers. And that's what he did. That's how he started out. He did that successfully for a couple of years. This is a typical statistic. And at the left end in 1986, that worked very well. Towards the end of that statistics in the early 90s, there were more and more issues with a statistic like that. Because there, as Gordon Bell lined up, there were more and more new companies with different architectures coming into the field, and they wanted to be counted too. Those were the manufacturers of these MPP systems and large-scale SIMD systems, thinking machines, N-Cube, Intel, and others. They wanted to be counted. And the vector mainframe manufacturers themselves, they had started producing smaller entry-level models for their own products as well. So the question, the never-ending discussion was, what is a supercomputer? What should be counted? What should not be counted? So we had to come up with a new definition of what a supercomputer is. Based on our experience, we wanted to have at least two things for that definition. We wanted to have a definition which would adjust itself over time by itself. So we didn't want to give a static threshold because we would have to adjust that every year to a new level. We didn't want to do that. And we wanted at the same time some sort of a procedure or some sort of a feature in the definition which would separate out concepts for machines from actual machines which were installed, because we were interested in compiling a real market survey as in actual functioning systems installed in the market. So the one data point which we had, which broke really the tie, we tried different concepts for 2 years. The one data point we had was really that we knew how many systems how many vector computers there were installed worldwide. And around 91, 92, we knew that there were more than 500 vector computers, vector supercomputers installed. So we were experimenting with lists, and this really was the reason that we decided we would compile a list of the 500 fastest computers. We picked 500 because we knew by our old definition we would have that many, and because it sounded sexy. Okay. The second feature we needed was that we needed a benchmark to really measure those systems. And we looked around, we compared different benchmarks available in those days, and Linpack was the one benchmark for which by a large number, by a large multiplier, there were the most results there, which meant we would exclude the fewest numbers of systems for lack of results. And that was one of the reasons that we decided on the Linpack benchmark, and we approached Jack, and he agreed to work with us on producing everything and putting everything together. So we produced the first list in 1993, and I looked up, I still have the electronic copy, a PostScript file from the first list. And on the first page we announced that we're going to do this quarterly, 4 times a year. And after we did it once, we immediately said, no, that's way too much work. We're going to do it twice a year. That's more than enough. And I think everybody who helps us compile those lists is very happy that we're not doing it 4 times a year. The one thing which we realized very early with the second list is that the real beneficial part of the data collection is actually trends over time and not so much the individual snapshots. And one caveat which I have to mention here before I go into some statistics about the list, is really that the top 500 is inventory based. So it gives you a mixture between the very new systems as well as systems which have been around for a couple of years but are large enough to be still counted. And for some statistics, that is actually beneficial, and for some statistics, it's actually not that helpful. All the information we try to have on the web as soon as possible. Sometimes we experiment with new categories and with new statistics on excellent PowerPoint, but if we feel like they stand the test of time, we try to get them back into the original database and actually publish it on the web. So this is probably the signature slide, which most people have seen or is most widely used, which simply shows the progression of performance over time for the 25 years for the 50 lists. The three curves are the total, the aggregate performance of all 500 systems. The red line is the number one system, and the green line is the end of the system. I'm not going to dive into the details of this. If you want to hear more about this and the traditional analysis we do, please stay for the BOF session, which starts at 5:15 in this room. But what I'm going to do is I'm going to try to aggregate all of those 50 lists now in one statistic. And I don't really like to do that based on system counts, because system counts puts a lot of emphasis on the end of the list, on the low end. But we're all about high performance computing. We're all looking towards the high end. So I try to do something performance based. But if I do that, then I face the blue line, which is 6 orders of magnitude from the first list where we had 1 teraflop to the last today's list where we have barely an exaflop, just over an exaflop. So I cannot take performance itself and add it up, because the most recent list would totally wipe out any previous lists. So what I have to do is I have to take each list by itself, and I have to normalize the performance value in that list. And there are different ways to approach that. What I did is I divide the performance of each system in each list by the mean performance of that list, by the average system size and performance of that list. I normalize the Linpack performance for each list, and that way I can add them up, because each list contributes the same overall value to my statistics. Each list contributes a total of a factor of 500, and if I have 50 lists, I actually have a total aggregate value of 25,000, which I distribute across my categories. So I'm going to demonstrate how this works, this normalized HPL and the sum of normalized HPL, by looking at the performance of the number one slides. And after I do this for the number one, I'm just going to show you the results for a couple of the categories we looked into. So this is very traditionally on a log scale, the performance, the Linpack performance of the 17 individual number one systems which we had in the 50 lists. There were only 17 systems which were number one at some point, and some of which you can't really see very clearly because sometimes lines overlap with each other. You see sometimes they get installed in pieces, but once they have the full size, you have a flat line because the performance of the system stays the same and until they are decommissioned. So the first step I do is I now divide the performance for each list by the mean of the performance on that list. And that's going to do two things. First, it's going to take that starting point of performance and bring it down for each system roughly at the same level. And second, it's going to slant my curves down. So this is the outcome. First, on the vertical list now, I have no longer a logarithmic scale, I have a linear scale. And you see each system gets introduced. If it's at full size, it's much larger than an average system in the list. And then its performance, its contribution to the list decays as the list catches up to the number one system. If you look at the left end of that curve, you see that in the 1990s, a typical number one system when it was introduced was about 30 to 40 times the size of an average system in the list. If you look to the right end of that graph, you see that the last 5 or 10 years, the typical size of a new number one system would be more like 70 to 80 times the average size in the list. So the number one systems compared to the average system have really grown in size, and that's something we have noticed over time because the distribution curve in the top 500 has changed. So that's one observation. Second observation is that all these curves actually look fairly similar in shape. There is a universality to it, but I'm not going to dive much deeper into that. So the second statistics I'm going to use is actually I'm going to integrate the area under these curves over the lifetime of the system. And the outcome of this is that you see new systems enter the list, they contribute merit, but towards the end of their lifetime, when the list has caught up to the system, that increase in contribution flattens out quite dramatically. So that's what you see. And you see a similar effect as on the last slide, that in the 1990s, the total lifetime contribution of a number one system was noticeably smaller than the total lifetime contribution of systems nowadays. That's mostly driven by them being larger and the market being more focused on the very high end. So now I'm going to show you 3 or 4 different categories. I'm going to show you the summary of that and dive into 1 or 2 of those categories in a little more detail. These Israeli statistics we don't show that often is where I take all the systems installed at a specific site and integrate them up. And I have done this for the normalized Linpack benchmark for all 50 lists. So you see there is a couple of very big sites out there that all have 4 or 3-letter acronyms. It actually turns out the 4 biggest systems on that top 10 list of sites are all Department of Energy funded and operated sites in the US. Lawrence Livermore National Labs, Los Alamos National Labs, Oak Ridge National Labs, Sandia National Labs. That's really a testament to what what a funding agency can do if they put high-performance computing as a priority on their research agenda and put their money towards that priority over time. The last 2, which is basically Dead Heat, NERSC, and Oregon National Labs, are Department of Energy systems as well. The next 2 ones, number 5 and 6, as well as number 9, are examples for sites which didn't exist or didn't have a computer when we started the list in 1993. Those were sites which at some point decided they were going to go into high-performance computing, and they got awards for big number one systems, and they basically started their life since then. They have accumulated quite a bit of cycles over time, but not quite as much as sites which have been in that business for a long time. The next 2 sites, as well as the last 2 sites, are special in the way that those are sites which have a lot of history, but they have never had a number one system in the top 500. So to be a number 10 site in the amount of cycles you have produced over the last 25 years did not require that you actually had to have a number one system at any point of time. And that is actually a quite nice statement, again, to the benefits of having a very consistent policy and a very consistent funding over time for something like this. This is looking at the 4 main DOE labs in the US and how they grew their accumulated cycles, normalized cycles over time. And you see, for instance, that the blue curve, Lawrence Livermore in the 1990s, they didn't have very large computer systems, and they started ramping up their computing efforts around 2000 and have overtaken the other labs since then. While on the inverse, labs like Los Alamos and Sandia National Labs, which were big in the 90s, they kept going on what looks like a steady pace, but they didn't ramp up the same way. That's why they are far behind Lawrence Livermore if you aggregate all 25 years. So now I'm going to show you 3 different categories which are more traditional. The first one is countries, and a lot of you are probably going to probably saw the headlines today that China is the number 1 in terms of systems, in terms of performance, and so on and so forth. If I aggregate all 25 years with these normalized performance values, it's very clear that the last 25 years, the United States was by far the dominant consumer of computer cycles overall. So that's not going to change very quickly. It's actually Japan is still very clearly the number 2, which is really a heritage from the 1990s, as well as from their efforts to produce very outstanding machines every 5 to 7 years, K-Computer, Numerical Wind Tunnel, and those systems, Earth Simulator. So United States first, Japan second, China already third, and I'm going to have a separate slide to that. And after that, European countries, Germany slightly ahead of UK, but UK includes some ECMWF numbers, which is a very big European site. And if the UK really leaves the European Union and we have to discount ECMWF from UK might go down. France is number 3 in that statistic. If I drill down just in the number 6 and show you this annual contribution over time, you see the US, the blue line on top, are rather steady, just declining a little towards the end. And you have to remember that my normalized HPL is a zero-sum game. Whenever something goes up, something has to go down because each list contributes only a factor of 500. So US going down, that comes in parallel to that green line going up. And that green line is the contribution of China, which indeed has overtaken or is on par with the US for the last 2 years. And you see Japan was very big in the 1990s, early 2000s, has slightly decayed or declined over that. But once in a while, they produce very big, spectacular machines, and they have a peak based on that. The next category is a special one, and that took a little bit of fiddling to get to the right classifications. I really tried to get a different handle on architectures again. And I tried to find categories which had meaning and are giving me a good signal. So I divided computer architectures into old styles SIMD machines like CM2s, which are at the very bottom, the vector computers, which are the number 3 in this list, which were the traditional vector mainframes, and then MPPs, and I split MPPs into Intel-based MPPs and non-Intel-based MPPs, and then I introduced the 2 categories are like about the most recent accelerated systems, basically MPPs with accelerators, co-processors. I split it out between NVIDIA and Xeon Phi and others. And if I do that, I see that over the history of the top 500, the non-Intel-based MPPs are actually the dominant class. It's not the clusters, which would be typically Intel-based MPPs, but the non-Intel-based MPPs. But that is because I have systems in there like the Blue Gene, like the IBM SP systems, like the thinking machine CM5 at the very beginning of the list, and things like that. If I look actually at how this evolved over time, these categories, I see a much richer signal. So here you see the normalized contribution from these system classes, from these architectural classes over time. You see the top 500 just started at the end of the vector mainframes. That's the green line coming down. And the blue line was jumping up. And the blue line was these non-Intel-based MPPs, which in those days were the CM5s and the N-cubes and the power-based IBM machines. And then with the advent of the cluster computing, commodity cluster computing in the mid-2000s, the red line jumped up, which is the Intel-based MPPs, while the blue line declined. So that's really when the commodity clusters took over. And the last 5 to 10 years, you start seeing the new classes, the accelerated classes, coming up, while the non-Intel-based MPPs slowly go down. So that's the trend there. If you do a chip nowadays, you do an accelerator, you don't do a main processor anymore. With that, I'm actually going to turn it over to Horst, who's going to look into the future.
Thank you, Eric. So what's next? So I want to just briefly, there are many things one could speculate. I talk about 3 different things: worldwide expansion of high-performance computing, applications, and new technologies. So you've seen probably variants of this slide, but it's, I think, always intriguing to see the worldwide use of high-performance computing platforms. This is by number of systems on the June list per country according to GDP. So you have the GDP, World Bank 2016, on one axis and the number of HPC systems on the other axis. And what you notice right up front is that China and the US, even with their June numbers, are way off the chart here, with 160 or thereabout systems, and of course with a GDP of the order of about $16 trillion. If you look at the average investment in the G20 list in HPC, that's the dashed line, and you see there are a number of countries that we've seen that have made consistent investment in HPC well above the list: Japan, Germany, UK, France, and some other countries also above the list further down in terms of GDP, such as South Korea and Saudi Arabia. And then you see another set of countries clustered along the average, such as Italy, Canada, Australia, Russia, and South Africa. But what I want to point your attention to is that there are a number of G20 countries that consider themselves being in the top of the world in terms of GDP and have a big say, but they don't have any HPC investment, such as Argentina, Turkey, Mexico, Brazil, India, who really are behind in their HPC investment. So you can say this is maybe also behind in investment in general, but if we take this correlation, I would expect that in those countries there will be rapid growth in high-performance computing, and that will happen hopefully in the next 5 years. And I would make another bolder claim out here, and I think that China, with 3 vendors being well positioned in some of those countries, making inroads and making sales, being very competitive as the Chinese vendors are now with the American vendors. So if you ask me in 5 years, will we see some countries like Indonesia or maybe Vietnam on the list? I would certainly say yes. And what machines will they have? Maybe Chinese machines. The second thing is I wanted to talk about a little bit more about applications performance. So we've heard this several times that HPL is not necessarily an appropriate measure for true application performance. But I want to show this slide again that Gordon showed already. That is the correlation to the best Gordon Bell Prize application performance. And actually, there is a very good correlation between the top 500 #1 and the Gordon Bell #1. Gordon pointed out already that there were the grape systems, where actually the grape systems performed better than the best top 500 list because the grape systems couldn't run HPL. But in general, the 2 curves track each other very closely, and so this goes back to Gordon's question really. Well, maybe the Gordon Bell Prize honors the application that tracks best high-performance Linpack. But I think it's important to see that the Gordon Bell Prize and top 500 really are closely correlated. So with that in mind, there are, of course, many questions. Here's another chart. I'll skip over this, running out of time. Of course, with many of these discussions in the last decade or so, there was this understanding that HPL was only one dimension of supercomputing performance, and several other efforts were started that are all represented here at this conference that were looking at other performance measures, such as power consumption, which really became a pacing factor about 10 years ago. We have the Green 500, graph applications for Graph 500. Then, of course, you heard about HPCG that Jack and Mike Carew started. And just very recently, IO 500 started up. Everybody likes to do 500. We always give the advice, as you heard, getting 500, even if it's just twice a year, and even if it's just once a year, is a pain. So the main advice I would like to give to anybody who contemplates a list is, let's start modestly. Maybe 50 is a good number, much better than 500. Anyway, Green 500 and HPCG are now integrated with the top 500, and you'll hear more about this in the BOF following right after this plenary. So of course, in this conference and many other venues, you've seen a lot of discussion about machine learning and the growth that machine learning has experienced in the computing world in general, but also on HPC platforms. Several new HPC systems have been announced that are using machine learning as a motivation, but focusing on machine learning. So that naturally leads to the question, should we do a machine learning ML 500? And that's a very fundamental question, and there are many questions that are derived from this. For example, is HPL maybe a suitable benchmark to characterize machine learning applications? Do we actually need a new one? But of course, we know that many machine learning applications are using lower precision, like 16-bit floating point. Many folks say, well, it's just matrix-matrix multiplication, so maybe Linpack is very good. We don't know this. We also don't know if any of these benchmarks might change the top 500 order. So our group has decided to make this an agenda for 2018 and work with the community and community input towards Machine Learning 500. And I put a big question mark behind this because maybe we'll walk away from this and say it's not worth it, or it's too difficult, or top 500 does fine. But here's an agenda. And again, if you're interested in this topic, stay for the BOF. We'll discuss that in more detail. Something that also is often mentioned is that cloud computing does not show up on the list. If you look at something like the Gartner report from June of this year, the market leaders are clearly identified. The top 500 list from June has one system, a number 438, the Amazon system on the list. We heard that recently Cray made an announcement that you'll get also Cray systems in the cloud. But in general, there is a very big divergence between cloud and HPC. And in particular, these are the public cloud or the commercial cloud vendors. Those private clouds, the systems that are used internally in Facebook and Amazon and Google the vendors are very secretive and don't tell anything about what they're running, what performance they get, what usage of clusters they actually have. So I think that I make it very simple and say clouds are not supercomputers. The application usage models are very different. And I would like to repeat what I think Jack said already before. If high-performance Linpack does not scale in the cloud, then don't expect real high-performance computing applications to scale in the cloud. I'd certainly like to hear, maybe also in the BOF later on, if you have any experience in this, because actually there are only a few studies that compare cloud performance in HPC systems. There was a study way back in 2010 about the Magellan Cloud, that NurseCat, that actually basically came to the conclusion that clouds at that time were not price competitive with HPC systems. I came across a very interesting study which compared 5 cloud vendors just recently using HPL, but they really didn't use supercomputing applications. They only scaled up to 1,000 cores. I think it's an ongoing point for discussion, but I think we should be very clear that clouds are probably at this point not useful for the traditional HPC applications. Lastly, of course, we are at a tremendous change, and maybe almost just like back in the late 80s, a lot of new technologies coming. There's experimentation with architecture. There's a question on post-Moore digital computing. We talk about quantum computing, quantum simulation, neuromorphic computing. So we expect a lot of things to change over the next 5 years or so. And so this, of course, again, raises the question, what is a supercomputer? And I think that is a definition that this conference, not just the top 500, has to really take into consideration, that as we go through this big change in architecture and technology, that we are actually at the beginning of a new era of supercomputing. And I'd like sort of to put this out there and give Alan Karp 1 minute to think about it. What is the $200 or $100 question that you want to ask in 2017 to stimulate the next 25 years of competition? But with that, I want to come to the conclusion. As I said, we're in this period of incredible growth of high-performance computing with some consistency that we've seen in terms of the systems. As you've seen from Eric, it's all MPP systems. Just to stop for a moment and think about it, 25 years of top 500 and 30 years of SC are truly remarkable. So we don't know what a supercomputer will be in 25 years. Just I told you all these possible new directions we could go in 2042, and we don't know how to benchmark it. And so I'd say also think about it, how you will be, I mean, if you'll still be around, I sort of hope so, but I'm not sure, how things will be in 25 years, in 2042. And so just trying to extrapolate to the future gives you a perspective on the 25 to 30 years that we're reflecting backward. What a tremendous journey it has been. And with that, I wish you all a good evening.
Let's thank the speakers. We have time for one question. There are microphones in the aisles. Okay.
How are they going to configure this?
I think I don't see anyone coming up, so let's thank the speaker. Oh, okay. Please, go ahead.
Hey, Jack.
Yes.
I think you deserve one credit. You have one slide missing, and that was you actually have a big part of the credit for helping develop the open source movement. You left out the fact that you and Eric Gross at Bell Labs developed the NetLib distribution system, where you could get open source software independent of our bureaucratic procurement organizations and our security folk and all kinds of other things, just by simply saying, send whatever. So I think you deserve a lot of credit. That was a decade before HTTP and all kinds of other things. And our managers who are clueless, thank God they're gone.
Thank you, everyone. Let's thank the speakers again. And there's going to be a top 500 birds of feather right here. Thank you.